let me start the evening session. Welcome to everybody. It is my pleasure this afternoon to introduce a new speaker of this week. He is Professor Sébastien Descotes-Genon. He is a prominent scientist in flavor physics. He started working on light meson dynamics in his Ph.D. that he took at the University of Paris Sud. And afterwards, his field shifted to B-physics from the postdoc from Southampton on. And he has worked since 2005 within the CKM-FITTER collaboration. He has done relevant work on CKM metrics. And it's about 10 years about that he works also on rare BDKs. He has been very quoted. He has about a 43 of H index factor, and he has from 2014 to 2019 he was the head of the laboratoire de physique théorique at CNRS with the 60 members in total, and since a couple of years he's deputy director of IJC Lab, CNRS, Université Paris-Saclay, Université de Paris-Orsay, with about 750 members in total. He has coordinated several EU grants and supervised several students. So I don't think I need to say more because I think most of you that works on flavor physics know him. So I thank again Sebastian for the lecture, and if you would like to start, I don't know if Fabio wants to add something.
Thanks.
Okay, so thank you very much for the introduction, Julia. Thank you for attending the lecture. Obviously, you heard that already from the other speakers, I guess. But that would have been obviously much nicer, and I would have been much happier to meet in real life with you and to give these lectures in Florence, also because I've never been to Florence, so that would have been a fantastic way of discovering the city, and also to interact with all of you, as well as Julia and Fabio, obviously. Okay, so life is more complicated. We've been learning that for 2 years. So you will have to do that by Zoom with me. I will try to keep the lectures relatively compact and to have some sort of break within the 2 hours, because maybe your attention keeps on, but my attention tends to be a bit fading after 45 minutes of talking and talking and talking. So we'll try to split a bit these 2 hours each day. And also, obviously, if you've got questions at any moment, you can obviously ask them. I know that there is also a specific slot at the end of the day where we can discuss also in more depth some aspects, but I don't think that is incompatible to do both. Okay, and the last thing that you will discover is that how badly I write. That will be a challenge for you, and I apologize already in advance for this. Okay, so if I try to see a bit how I'm going to split all the time that we've got together. So I will probably start with an overview. So especially how flavor arises in the standard model, because that's obviously the first point, and that will take us quite a bit of time today. So to understand what are the various parameters involving flavor, I'm going to focus mainly on quark flavor. I'm going to talk very briefly about lepton flavor in some cases, but my main topic here will be focused on quark flavor physics. On the way, we're going to see find again CP violation. We're going to find again interest of rare decays, and also some of the challenges on the way. And then I would like to discuss with you a few theoretical tools that will be needed, especially things related to the notion of effective theory, effective Hamiltonian, as well as the idea of non-perturbative inputs, so inputs related to the dynamics of QCD in the non-perturbative regime. That is an issue that we keep on encountering quite naturally in flavor physics all the time, as well as, if time allows, a few more tools that are of interest. Then that will be the time to move on to the determination of the CK matrix, with the determination of the various elements of the CK matrix, and also come back to the various notions related to CP violation. And I think that they're going to be quite interesting, especially because of the fact that we will have a comeback from B factories due to Bell2 after the era of LHCb in the field. And then I will move to what has been called by the people in the field anomalies. So these are not the anomalies that we tend to think in terms of a breakdown of classical symmetries at the quantum level or something like that. It's much more mundane. It's deviations, unexpected deviations that occur in some B decays that are been going on for a while and that are a focus for quite a large part of the community now. And now, and to finish, a few new physics considerations. So how do we put together the fact that we do have an overall very good description of flavor using the standard model, but also deviations that seem to arise here. So how do we, are we able to put them together, both at a general level of effective theories, but also in terms of specific solutions when we're dealing with the new physics, the big quark anomalies? And I think that if we're able to cover all this, then that will be already quite an achievement. We'll see whether we can do that. Okay, so for the moment, what I want to discuss with you today is an overview of the situation, and especially the standard model situation. And so I'm going to repeat quite a few basic things concerning the standard model, but I think that they are quite useful, both to have a clear idea of how flavor arises in the standard model, and also when we discuss generalization, extensions of that, that's also useful to keep in mind what were the ingredients that we put inside the standard model to get the pattern of flavor that we're finally observing. So in general, as you know, if you want to, if you want to have a description, especially for the standard model, but in general for particle physics, so what you would use is quantum field theory, so just special relativity plus quantum mechanics. And then the central elements of this quantum field theory will be the Lagrangian that you will just derive by considering gauge groups, a gauge group that will fix the symmetries that you have that will lead to the interactions that you need. Then you have a field content with representations associated with this symmetry group. And then, if needed, and in the standard model, we know that we know it, a symmetry breaking mechanism. On top of that, you have the question of building a theory that is renormalizable. So this is actually a question that you can discuss in two different directions, because from the initial requirements for normalizability, you could see that as being essentially a mathematical statement that was related to the question of getting rid of all the infinities occurring once you were discussing the loop level, in a way where you didn't have to introduce at each order more and more quantities to absorb these infinities. But nowadays, and that will keep on popping up again and again when we're discussing flavor, there is also a physical requirement, which is a bit different, is to see this theory that you're writing down as being some kind of low-scale version of some underlying theory. And the fact is that because you've got an evolution of the parameters describing your theory, when you go from the high ultraviolet version of the theory down to the infrared version that we experience, then you will see an evolution that will tend to reduce more and more the parameters that correspond to terms that are not renormalizable. So in the end, you find that you can live in a theory at the low level that tends to be a renormalizable theory, even because of this evolution of the parameters in front of all the operators that would correspond to an higher dimensions. I'll come back to that later. But okay, and so this has been put inside the standard model description, which, as you know, has been very successful, but is a bit annoying, both because of the structure, which is a bit contrived, and also because of the large number of parameters, which, on top of being a large number that have been to be set by hand, are also obeying hierarchies which are difficult to understand from first principles. And actually, for this part, so for an explanation of this, you would like to, well, you've got obviously many ways of trying to address this issue, but one of them is to look for the sector where you've got most of them. And actually, that's the one where you start discussing flavor, because we'll see that you've got many parameters describing the flavor sector compared to what you have in the gauge sector. So if I go back to the three elements that I've outlined for the standard model structure. So as you know, all of you, sorry, you've got a gauge group, which is SU3 times SU2 times U1. And then you have to look at the matter fields, so the fermions, and to determine their properties, transformation, representations under this gauge group. And the point is that, and that's going to be something which has a huge importance for the standard model, is that you make a difference between the chiralities of the fields. So it's a chiral model. And so you have to distinguish between the chiralities. So you got, if you have a fermion field, you can just project out the left and the right-handed chiralities just by acting with the two projectors involving the gamma 5 matrix. And in the massless limit, these two chiralities, which are defined in a Lorentz invariant way, so that's an appropriate way of separating those elements from the point of view of a theory that wants to have a special relativity embedded. But in the massless limit, then you have an identification with the concept of helicity, meaning how the spin of the particle, half spin of the particle, is going to project with respect to the momentum of the particle. Obviously, as soon as you've got the fact that you need to be in the massless limit is because you cannot get into the rest frame, and so you cannot change the value of the momentum by going to one rest frame and then going from a boost and then applying a second boost, so that you would mix the helicities this way. And so, but in the massless limit, it's not possible, and so the distinction remains valid in any frame, and so you're able to make the identification between chiralities and helicities. Oops, sorry. I have to. That's my first lecture using this kind of medium, so in some cases, I hope I'm not going to break down the iPad I'm using during the lectures. Okay, and so since we're making the distinction between the left-handed and the right-handed chiralities, then we can see that indeed, when you look at the standard model and the representation of the various fields regarding the representation under color, under the SU2 left, and then the hypercharge, then you do have a distinction between the left-handed quarks, for instance, the up and the down quark that you put inside a doublet, and that has a sensitivity, so it transforms as a triplet under SU3, and then the fundamental for SU3, and then a doublet for SU2, and then a hypercharge of 1,6. Whereas for the right-handed quarks, then you do have, sorry, I shouldn't have put an equal, then they live their lives separately with under SU2, whereas they are still sensitive, obviously, under SU3. And then the same thing will go for the leptons. Then you put together the left-handed neutrinos and electrons, left-handed, inside a doublet, once again. No transformation under SU3, whereas you've got the right-handed electron being just sensitive to the hypercharge. And then in principle at that stage, there is no right-handed neutrino. That could be introduced, but that's something which has no interaction, so it would be just for mass purposes. Okay, and then, as you already noticed, I've introduced an index I, which corresponds to the generation, so that you got the fact already at this level that you got 3 generations in the standard model. And so the fact that you need to have those generations to come together with those numbers, at least fulfill some requirements related to what is really the anomalies this time, meaning the fact that you don't have any breakdown at the quantum level of the symmetries that you have implemented at the classical level. And so you need to have these combinations to pop up all together, otherwise you would have problems fulfilling this requirement. Obviously, you could add other fields with other representations, and then you have to work out whether they also fulfill these requirements. But from the point of view of the standard model, if you want to add some quarks and leptons behaving this way, then you have to put the full gamut of a whole generation, and you cannot just pick and choose what you want concerning the content of your theory. Now the question, why do you need 3 generations rather than 1 or 2? That's something that, as far as I know, nobody has the answer to for the moment, but that's obviously an important question that you at some point we would like to I think I stopped sharing my screen.
Yeah, we cannot see your screen any longer.
Okay. I told you that there would be some up.
Perfect. Now it's fine.
Perfect. Thanks. Okay, and then the last element, and that's probably because everything broke down, is symmetry breaking, indeed. So the fact that you don't want to keep at the lowest level the whole SU2 left cross U1 symmetry, but you want just to keep the U1 electromagnetic, and this one is related to the dynamics of the Higgs fields. And so that's a doublet that you have to introduce. And actually, because the doublet representation is a pseudo-real, you can actually define a very close friend to this doublet, which actually is exactly has just the opposite transformation, anti-doublet, compared to the doublet of the Higgs field. And that's going to be useful when we start discussing the interactions of the Higgs field together with the various fermions. Okay, so now that we've got this, we can just write down the Lagrangian. And don't worry, I'm not going to write it in the full form. First, because that would be too painful for me, for my hand, and probably for your eyes. So in the end, what you have is something with different elements. One, which is just the gauge part. And so this one is, if I want to write down what it would look like, that would be something that involves the various field tensors associated with each of the gauge groups. So this one is just involved in the dynamics of the propagation and interaction of the gauge groups, of the gauge fields altogether. So especially the fact that you've got your free gluon or free WZ and so on interactions, and 4 gluon and 4 WZ interactions. You've got the Dirac part, which is very simple at that level because of the structure that we have concerning the symmetries, meaning that you don't have any, as you know, any mass term that is present here, because this mass term actually would be something like psi left, psi right, and as we discussed already, we make a distinction between the left and the right handed fields concerning their representations and other various subgroups of the gauge group. And so the only thing that we have is a term which is, so for all the fields, that's going to be something that separates the left and the right through the covariant derivative. And this covariant derivative is also responsible for the interaction between the fermion fields and the various gauge fields. So on the way, I'm just introducing a bit the notation. So you've got the gluon field G, W associated with SU2 left, so 3 of them. And then you've got B nu, which is associated with the hypercharge. and then GS, G, and G prime being the coupling constants corresponding to that. And then the last part is the Higgs part. The fact that, so the sign of the mu squared is the term which the would-be mass is actually the reason why you've got this shape, this Mexican hat shape of the potential, and the fact that the minimum corresponding to the vacuum expectation value of the Higgs is going to be different from the naive vacuum expectation value. And the fact is that, so this, the fact that you've got this term here, it triggers the electroweak symmetry breaking. That's going to give masses to the W and the Z. Actually, the fact is that, so in your doublet phi, you had 4 degrees of freedom. If you think in terms of 3 degrees of freedom, 3 of them will go into the longitudinal polarizations of the W and Z, since you need those polarizations when you do have gauge bosons that are massive, that become massive due to a symmetry breaking. And then you've got 1 remaining degree of freedom, which will be the Higgs field, the part of the Higgs field corresponding to the Higgs boson. Sorry. Okay, so when you do that, so you will have to actually, since you give mass to the W and the Z, you have to express the fields that you had at the beginning, W1, W2, W3 corresponding to SU2, and B mu corresponding to U1. In terms of the physical degrees of freedom that will correspond to W plus minus, then mu and A. So that's not very complicated. If you just introduce the vacuum expectation value of the Higgs field as being 0 and V over square root of 2. So actually, you can use the gauge transformations to bring you to this expression. In general, that could be anything, but you can actually get back to this expression and do the expansion, fixing your convention so that you are at this particular point along the circle of equivalent solutions of your potential. Then you can express very easily your various minus plus. So the W plus, the W minus, and then so you put together W1 and W2 in order to get the plus minus W, and then you have to put together W3 and B in order to get 2 different combination, orthogonal combination, which correspond to W3, sorry, that's G and U. So with masses that can be expressed in terms of the vacuum expectation value and of the Higgs, as well as the coupling constant. And then the point is that because you still have conserved, because of the way you broke the symmetries, one particular gauge group, which is the electromagnetic subgroup, then you still have one of your fields, gauge fields, that are massless, as expected. And so derivative that you had before, you can re-express it again in terms of these various physical gauge fields. So you've got an interaction potentially with W plus W minus, then with a Z. Oops, sorry. And then with the photon and with a connection between the various couplings that you had for SU to left and U1 hypercharge and the electric charge, as well as an expression of the charge that involves both the representation under SU3 and then the hypercharge, as well as the term needed, sorry, needed in order to see the interaction between W plus and minus. So that means that you go from one up to a down or an electron and a neutrino through W's, whereas you stay as expected inside ups or downs, electrons, neutrinos, only when you have an interaction with a Z. I forgot the sign here. Okay, and the last thing I should have put is the expression of the Weinberg angle in order to be complete. Okay, so this, going back to the Dirac Lagrangian, we can read from this the interaction between the fermions and the physical gauge bosons. And so if I write down, so I will have terms that will correspond just to, I should probably write that. So I'm separating the part that correspond to the derivative without any, this time I'm separating the part which, in the covariant derivative, the part which is the naive derivative, and the part that correspond to the interactions between with the various gauge fields, physical gauge fields. Plus d bar r slash dr. And then I got the term that I'm interested in, and that's going to be the point of interest for us, which is how, to which current the various physical gauge field, gauge bosons are going to couple. So it's just re-expressing the various W1, 2, 3, and B in terms of W plus, minus, Z0, and A mu, so nothing extraordinary. And then what you have is just terms corresponding to the coupling to the charge bosons. And then we've got something which is more complicated concerning Z. And then you've got the say. So this was for the lepton part, and then you've got a similar situation when you're discussing the up or the down quarks. And then finally, you do have the electromagnetic part, as you would have expected from the beginning. So here we're putting together contributions from the left and the right. In a way, we could have re-expanded and say that's E bar R gamma mu minus 1 ER plus E bar L gamma mu minus 1 EL, and so on for the other terms. Okay, so what you can see from this is that here you've got charge currents involving only left-handed fermions, whereas on this side you've got neutral currents with left and right-handed fermions. And the last thing is that you see that, as expected, you got the same coupling of the photon to left and right. And actually, that's going to be quite important that we do have for the W plus or minus, only the left-handed component being part of the discussion. So now the thing is that for the moment, what I've written is that's the expression for a single generation. I introduced before indices, but for the moment, here I've just written what was done for a single generation. And if you remember, I obtained those expressions just by considering the Dirac-Lagrangian. So in principle, since when I start putting the generations, I would have to put the same index for psi bar and psi here. So that means that here in the expressions I've written, I've got generation indices that are implicit. But actually, I should just consider that I have to do the same thing, meaning if I want to put the generation indices everywhere, I should start putting them for nu bar left I, gamma mu 1/2, nu L I, and so on and so forth. So I have just couplings within a generation. I don't have couplings between generation. That's in particular correct when you're looking at W plus and W minus. For the moment, I got a transition from a D-type quark to an up-type quark, or the other way around, or the electron and the neutrino, but that's still inside the same generation. But on top of the fact that we know that it's not the case in practice in real life, the problem is that these expressions are true for physical gauge bosons, but we have not discussed for the moment the question of the physical degrees of freedom for the fermions. In other words, what are the mass eigenstates of the fermions? because we did exactly that to determine the physical gauge bosons. We just look at the, actually I didn't recall that, but we just looked at the various mass terms for the gauge bosons that were actually created by the terms d mu phi after electronic symmetry breaking, after there is a vacuum expectation value of the Higgs field. And we diagonalize and we get the various gauge bosons that I just showed. But so we stopped halfway through here, and we should not. We should keep on and express and have a look also at what's going on for the mass eigenstates for the fermions. And that's only once we have re-expressed those currents in terms of the physical mass eigenstates of the fermions that we will have completed the task of having expressions that are okay from the point of view of physical states, physical quarks and physical gauge bosons. Okay, so we can just do it. And how do we, where should we look for that? Well, if we want to look at the mass eigenstates for the fermions, then you have to look at the Yukawa part that contains the mass terms that we are after once electroweak symmetry breaking has been considered. So this Yukawa terms actually, so if you want to, and this time we're going to keep explicitly the various indices for the generations. So if you want to write down something that, so these Yukawa terms, they correspond to an interaction between the Higgs field and a left-handed part, left-handed doublet, and the right-handed singlet from the SU2 point of view. So that's exactly what we want. And that's what it was why it's very interesting to have these Yukawa terms to generate a coupling between the left and the right, which is needed for the masses. And so here I just written the case for the electron and the leptons. And then you do have also Yukawa couplings that I do not why between the left-handed doublet for the quarks and the D-type quark from with the right chirality. And then the last element is also that you can write down a coupling between the same left-handed doublet and the right-handed singlet for the up-type quark, but that's because of the fact that we're using, so we can express that using the same Higgs doublet because of this pseudo-reality of the representations of SU2 that allows us to involve exactly the same. If we were considering different gauge structures, then we would not be able to have the same, to necessarily to involve the same Higgs doublet for both down type and up type quarks. And once again, in this version of the standard model, for the moment, since I decided not to take into account the right-handed neutrinos, I don't have any terms, equivalent terms that would generate a mass term for the neutrinos. Okay, so now if I just take into account the fact that there is a vacuum expectation value for my Higgs field, so I just expand my theory around this value. So I just keep this constant term, and then when I do that, what I will end up with is just a term that is a mass term, correspond to a mass term, coupling the left and the right chiralities. It's not yet exactly a mass term, but so for the moment, okay, and I forgot to specify that obviously you've got the hermetic conjugate everywhere. So for the moment, I don't have any requirement concerning the UKWs. They can be anything in principle. And so if I want to now to be able to express this in a way that looks like a mass term, I have to so diagonalize, but actually that's not really diagonalizing, it's more writing a singular value decomposition. So you've got these various Mij with a capital M, and as we just discussed, they just come straight from the UKWs multiplied by the vacuum expectation values of the Higgs field. And then you say, okay, I can always express them in terms of two unitary matrices, and here, not necessarily the same ones. They would be identical if we were in presence of a matrix that can be diagonalized, really diagonalized directly, and then with a diagonal matrix containing the eigenvalues. And so that means that my mx that I write as mx1, mx2, mx3. So you would have, for instance, if I'm looking at the U-type quark, that should be the masses of the U, the C, and the T. G, that could be D, S, P, and for the electrons, obviously, electron muons. And so now when I do that, so that means that I can take out the two unitary matrices and use them to redefine the fields so that in the middle there is only the mass, which is the diagonal that is present in the result of the Yukawa Lagrangian after electrode symmetry breaking. And then, so I have just, quote unquote, to redefine. So I put, for instance, all the three up-type quarks together, UCT, in a flavor triplet, if you wish, separating the left and the right, and then I will redefine what I call UCT left and once, and UCT on the right by just multiplying, saying that's actually corresponding to the physical version, but with the multiplied by this arbitrary unitarity matrix. And I can do the same for DSB and DUT. In principle, I can also play the same game with an arbitrary matrix for neutrons. Okay, so now what's the impact of that? So if I'm looking at the Dirac term that I had, sorry. So the term in the Dirac Lagrangian, that the kinetic term in the Dirac Lagrangian, or if I'm looking at G mu, at the couplings, the currents coupling to the Z or the A, then what we have is actually a structure that you can separate the left-handed and the right-handed chiralities. And you can use the fact that they have exactly the same structure for the free generations. That's exactly what I said before, that you can actually thinking of putting summing over all the free generations, and you will have just terms that correspond to the first generation, then the second generation, or the third generation. So in the end, those terms, they all contain structures that are of this form, where psi x is either UCT or DSB or E mu t. That means that you don't have any discussion between the various generations. It's just a summation. And then if you just do, so you would have in the end, U gamma mu U left gamma mu U left plus C left, C bar left gamma mu C left plus T left, T bar left gamma mu T left, and so on. And so if now I'm thinking of turning using a unitary rotation in order to turn separately what I have in UCT left and UCT right, you see that actually those two terms, they remain absolutely identical, because if I do this redefinition, I will get something which will be involving on the left and on the right exactly the same structure. So because of unitarity, those two contributions will cancel. And same for obviously for R. So that means that the redefinition we're discussing in order to get physical masses coming from the Yukawa term, actually, they don't change anything concerning the structure of the kinetic Dirac term, or the coupling to the Z, or the coupling to the S. On the other hand, if I'm looking at GW plus, so the coupling to the W, then what I would have is something quite different, because since I do have a different field involved on the left, on one side and the other side, just because it's a charge current, then you do have terms that will start mixing generation. And so the fact that, so you see that you don't have necessarily the same structure on both sides. And I mean, you don't have necessarily the fact that this combination of unitary matrices, in general, they're not identical to unity. There is no reason for them to be identical to unity. At least if there is a misalignment between, for instance, VUL and VDL. And since we started from something which is in principle arbitrary, obviously you may hope that if you have some knowledge about the underlying theory leading to the standard model, you will be able to get some idea of why the Yukawas are the way they are. But from the standard model point of view, you don't have any reason to know something about that. And in general, you would believe that these two matrices, rotation matrices, are going to be different. And so that here in the middle, you will have something which will be different from identity. So you get on one side the so-called PMNS matrix when you're looking at neutrinos. So that's Pontecorvo, Maki, Nakagawa, and Sakata, sorry. And then on the other side, for the quarks, you got the CK matrix, the Kabibo, Kobayashi, and Mascot. Okay, so the fact is that, and so obviously for the W minus, you get exactly the same thing. And actually, that's going to be just the hermetic conjugate. So the same matrices are going to be involved on both sides. So the thing is that the point is that even though on the paper that looks exactly the same discussion on both sides, the question is whether the mechanism for the mass generation is going to be necessarily the same. And the answer is for the neutrino that we don't know exactly what's the current situation. So for the quarks, as far as we know, what I presented is the full story. So you have only the mass terms derived by the Yukawa and connecting left and right, and so corresponding to Dirac mass terms. And so if you do have that, you just wrote down everything, and then you get something which will be the CK matrix. If you start having additional possibilities for the mass generation, and that's possible for the neutrinos because you got this fact that you can write additional mass terms on top of the Dirac mass term, which will be Majorana mass terms, due to the nature of the couplings of the neutrinos in the standard model. Then you have the additional higher order operators that you can write from that. That means that the discussion of the structure of the PMNS matrix is more complicated. You have to first decide some aspects of make more precise what you believe to be the generation mechanism for masses in order to be able to make statements about the structure, detailed structure of this PMNS matrix. And that will be in relation with that, with those assumptions concerning the masses. So PMN, as I said, the PMNS structure depends on the assumptions on the mass generation mechanism. And so now, for the moment, I will focus on the CK matrix. Okay, so I've already spoken for 1 hour. So one thing, since I said my concentration might slow down at some point, so I would ask you if there are questions up to now. And if there is none for the moment, I would propose that we make a short break of 10 minutes so that we can refresh ourselves and then keep on. You had a nice break. So we restart the discussion. So as we just saw from the discussion of the properties of the standard model, we end up with having to perform the expression of the standard model in terms of the physical degrees of freedom of the theory. And so in particular, we end up with discussing the interaction between the weak gauge bosons and the fermions, diagonalizing as much as possible everything, and ending up with having two different situations. When we're considering couplings that are neutral currents, so coupling to Z0 or mu, then we don't have any crosstalks between generations. And so that means that you remain with the same, actually with the same quarks or the same leptons when you're interacting with through a Z or a photon, which is quite fortunate, especially considering that otherwise that would be a huge blow to the description of quantum electrodynamics. And On the other hand, we do have a rather different situation for the charge currents, because we saw that the potential, when we're doing the diagonalizations, the misalignment of the rotations needed to diagonalize the up and the down quark mass matrices actually allow one to have a crosstalk between different generations. And so, as we just discussed before, and if we try to put now in terms of diagrams with actual eigenstates, mass eigenstates that are appropriate, then you have couplings of this kind involving, so for instance, up and down of the W plus and the W minus. And the fact is that, so you do have, so I'll remind you that these are the generation indices. And the fact is that because of the fact that you have a Lagrangian that must be real, you have a hermetic conjugation. That means that you have V for W plus, but the complex conjugate for W minus for the Sikane matrix. And as I said before, so V is not necessarily the identity. Naturally, we'll say that it is not, exponentially speaking. Okay, so now the next, so that's the first thing. The second thing is that, as I said before, only left-handed fermions are involved. And so that raises the question of the properties under the various discrete symmetries that we know to be interesting to discuss when we're discussing the case of fermions of spin half. So we've got CPT, which are the discrete symmetries that are interesting when you're discussing arising naturally when you're discussing the Dirac theory of spin half fermions. And so clearly for this kind of Lagrangian, P cannot be satisfied just because you have only left-handed and not right-handed fermions being involved. The question that historically has been a long-standing issue is to know whether CP can be a good symmetry for this. And actually, the answer to that is directly related to the properties of this coupling, because for the if you apply CP to this Lagrangian, corresponding to the interaction of the W with various charge currents, then you see that actually, because of the properties of the bilinear Q bar, gamma mu Q under CP, the only thing that happens is that actually you're swapping the positions of the various of your two fermions. And so you can end up with something which is very much the same as before. And also you change W plus into W minus. And that means that in the end, you get something which is identical to the initial Lagrangian if your CKM matrix is real. It's just that we swapped the places here because of the transformation under CP of the U bar gamma mu D and D bar gamma mu, sorry, gamma mu U. And then you end up with something that looks very similar, but because of the hermetic conjugate that you had at the beginning, that means that you got V and V star exactly at the opposite position compared to what you had initially. So that means that the invariance under CP holds only if the CK matrix is real. So now one interesting thing to see is to have a look if that's something which is necessary, possible, imaginable. And so the thing is that we started with a CK matrix that is arising from this diagonalization of the mass, the Yukawa matrices initially. But then, so in general, you would say, okay, so there probably, and then even it's very likely that there is actually an imaginary part, but actually you can quantify in more detail how many parameters you need in order to describe this CK matrix, and especially how many sources of CP variation are contained, meaning how many sources of imaginary parts are present in this. So there are two different ways of getting the result, and I think I'm going to present both because actually they're quite interesting for different reasons. One which is a simplistic argument, and the other one which goes a bit further into the symmetries of the standard model and the flavor symmetries of the standard model and their flavor transformations. And for the discussion of new physics, that can be also interesting. So I'm going to present that. Okay, so the simple version would be just to say, okay, VCKM is an n by n unitary complex matrix. So it has 2n square real parameters. And so if I'm just looking at the expression, I could just say, okay, it has each entry has a modulus and a phase, and that's it. But then I can use the fact that it's a unitary matrix, and so I've got relations of orthogonality that are present. And actually, I can write relations of orthogonality involving the product of the same row or column. And so that means that, and you got so n relations, but you know that this kind of relations, it's just it's this modular, the sum of moduli squared. So actually, those n relations have give only one condition each, because you know that there are no imaginary part. It's only the value of the real part that is present. And you got also relations of orthogonality involving the product of two different rows or columns. So that's the same. And so if you do the algebra, you see that you got n and minus one relations, but this time they are really among complex numbers. So you've got two conditions each. When I think in terms of conditions, I mean conditions between real numbers. So we are taking the real and the imaginary part. And so doing this, I've got two n squared terms. I have one n relations corresponding to one condition for each relation. And then I've got two conditions for n and minus 1 over 2 relations. So in the end, I've got n squared real parameters. But so that's you would say, okay, that's the end. But actually, you can go a bit further from this. So this was by taking this as starting from just the requirement that it's a unitary complex matrix. Then the second thing that you can do is to separate in that how many moduli and phases are inside these n squared parameters. And to do that, you can just say the moduli can be obtained by considering the real orthogonal matrix rather than a unitary complex matrix. And this way, you have no phase, but you have still the conditions. And then what happens is that then you got n squared real parameters, n relations with same row or column. Same with diff n and minus 1 over 2 with different rows and columns, but this time it's everybody is real. So you've got one condition in each cases. And so that means that when you do the same computation, you started with n squared, you're removing n and minus 1 over 2, you end up with n and minus 1 moduli. And so you would say, okay, that means that since I've got n squared in total and I've got n and minus 1 moduli, I have still n plus 1 over 2 phases. Yes, but there's still a freedom that we have not used at all for the moment. And there is still a freedom in the phases. We can remove the phases of the fields because actually at this stage they don't carry some information, so we can remove them. Actually, we can remove n minus 1 phases. And so that means, because if we remove, we turn around everybody, that would mean that we have made no change and have not redefined anything. And then that means that in the end, we get n minus 1 and minus 2 phases here. Okay. And so that means that in the end, we've got for n equal 2, we've got only one modulus, but 0 phase. So that means that actually when we are with 2 generation, we have no CK violation. And that means that your CK matrix can be expressed as a very simple rotation matrix. where the parameter that you have inside is just the Cabibbo angle. Whereas for n equals 3, you got 3 moduli and 1 phase. And so that means that then CP validation is possible. So that was in another language, the comment from Kobayashi and Maskawa, meaning that once you got 3 generations, then you start having the possibility of having CP validation, meaning that you cannot, in general, remove all the phases, and there will be one phase that contains physical information, and that corresponds to a generation of the of CP validation. Okay, another more fancy way of seeing that, because that's the simple way. It's is to start a bit earlier. Actually, it's to say, okay, I can look at the situation already at the level of the Yukawas. Because if you think of it, you've got a very large flavor symmetry group. So it's not a gauge group, it's not a local group, it's a global group. Just by doing this kind of redefinition that we already used for the when we discuss this unitary matrix mixing the various generations, we can actually think of applying similar rotations on the various objects, various fields that we have considered. So you could imagine to apply that to. So if you consider the Yukawas of the quark fields set to 0, then you've got a very large flavor group, because actually you could think of performing a rotation, a U3 rotation on the quark fields, the quark doublets that have, so that are inside the QL doublets. You can imagine to do separate rotations concerning the up right part, and the same thing for the down right type quark. So I insist these are rotations in the flavor space. So you're rotating between, for instance, if you're considering the second part of the second one here, that corresponds with 3U. That would correspond to putting UCT in a right inside a column and performing transformation rotation between those components. And same thing goes for D, and the same thing goes for the contributions to the left-handed doublets in Q. Okay, and so actually if you want to, so this flavor group is broken down to a very small group once you start having the Yukawa putting inside. But before doing that, you can try to break down that into a structure which makes the discussion a bit simpler. You see that you've got here U3 matrices. Actually, you can separate the parts corresponding to SU3 that we're more used to. And terms that will correspond to phases. And I will just spend a few minutes discussing what they are. So those guys here, they're just exactly what we discussed before. So I've got a unitary matrix, a SU3 matrix. So for instance, as I said before, the rotation of UCO2 here. Okay, and then now you've got the various phases. So you've got one which we put B because that's a global phase redefinition associated with a baryon number. So that's typically you just rotate by the same amount everybody. Psi is just all the quark fields. Then you've got one phase redefinition that is associated with quark hypercharge. And so that's just here why it's just the hypercharge for psi left or right. And then you've got a last one, which is a global definition just for DR type quarks. So that's something that was discussed in particular by Peche and Quinn in other environments. And so that's why it's called PQ here. So I'm just doing the rotation just for those guys. And so this is giving you, so why do we choose to have this this Fermi decomposition? So the most important one is just because we know that the baryon number is going to be important and we want to keep it. The two other ones are just a common a way of separating the three phases that are present in U3, the three U3s, and then you want to extract them. So you have to define and separate them, keeping the baryon one isolated, and the two other ones are a useful decomposition. You could imagine other ones. Okay, and so the Yukawas break down this. So we started with this huge symmetry, but then in the end, the only thing that remains corresponds to the baryon numbers. And so when you look at the situation, so you had, if you think in terms of the number of parameters that are needed in order to describe the groups at the beginning and at the end. So in terms of real parameters, in terms of imaginary parameters. So you started by, so each of the group you started on. So each of the three groups, you need 3 real parameters, 6 imaginary parameters to start. And then in the end, the only thing that remains is just a phase. So you have only one here. And then what you have is that this is triggered actually. This breakdown is triggered by U, Y, and YD containing both 9 entries each with a real and an imaginary part in each case. So actually, when you count the number of broken generators that are present here, after you did that, you can count the number of physical parameters remaining. So you started with, so you see that in the end, you remain with, so you got 9 real parameters that are left after the breaking. And so that corresponds to 6 quark masses and 3 secant parameters. And then if you look at the imaginary parameters, you remain only with 1 phase, which goes into the secant. And so that means that actually you do have, so that's an agreement with what we said before, you do have indeed for 3 generations 6 quark masses, which is what you expected, but more importantly, 3 secant parameters and 1 phase that goes also in the secant matrix. So that's the confirmation that you do need, in general, unless there is some kind of funny accident, you do have a source, and actually a single source of CP violation inside the quark sector. So, okay, so that's for the, and that's related to the secant matrix arising in the charge current. Now, there is one thing that I've not discussed yet for the generalities, and that's the case of the neutral currents. Because what I just said is that at tree level, we were quite fortunate. At least we had this situation where if I got a photon or Z, and I start from the field from a generation, I remain with the same field from the same generation. I don't have, so it's, there is no crosstalk between generation. It's inside the generation. So typically, for instance, you do not have something like a Z, a B, and a S. So jumping from the third to the second generation, that's not possible in the standard model. So there is no favor changing currents, neutral currents in the standard model. Obviously, immediately you have to wonder whether this is true in generality, and indeed there is a caveat. That's only correct at the tree level. That means that this is not something that's something that we discuss through this path of diagonalizing, extracting the mass eigenstates, looking at the various couplings to the various generations and so on. There is no guarantee a priori that it would be some kind of general symmetry unless we impose it from the start. And so you can imagine at the loop level to do something that would be able to do this kind of transition. So if you have a W that is emitted from the B, and then you have an uptight quark that goes through, emits a Z, and goes back, reinteracts with the W to give you an S. There is no, that's not impossible to have this, just that it's a loop process. And actually, that's a loop process which is very much suppressed in the standard model. So it's for several reasons. So the first thing is that, as I said, it's a loop process. So you have to pay a price in terms of G squared over 4 pi squared that will suppress the contribution compared to something at the tree level. But there is more to that. In that, if you look at the terms that are involved here, you see that you have two W interactions. So that means that you've got CKM terms that will be present. And actually, if we neglect the mass differences, imagine that we live in a world where the charm and the top are equal. Then the contribution of the free loops would be completely identical. You would have a contribution which would be something, whatever, multiplied by the product of the CKM matrices. And so you've got, since it's a down to up and then up to down, then you've got V and V star contributing. You've got B and S on each side, and then you have to do the sum over all the possible internal loops. And then, as I said before, since we're considering the limit where all the masses are equal, then that's the only difference. All the contributions remaining are equal. And this is actually 0 because of the unitarity of the CKM matrix. So that means that actually so that's a G mechanism, Shouliopoulos-Mayani mechanism that leads to a suppression of this kind of contributions. Actually, if you want to be a bit more precise, actually, so that means that what you have for the amplitude so if we make the distinction between the various contributions, so that means that actually we have to make a distinction. And there will be the only part that will survive will be a part which is dependent on the masses, because any part which is not dependent on the masses will cancel due to this unitarity of the CKM matrix. And so I've just put the masses of the quarks divided by MW. Actually, so what you can show is that, so you can do the computation, but actually you can even guess what will happen, is that this will be linear if the mass of the fermions is much smaller than the W. Actually, that's what you would expect, because this kind of contribution, when you send the W mass to infinity, you should expect decoupling. So this term should actually be suppressed. And the only thing is that the decoupling does not work for MT. So actually you will have something that will be more or less, because MT and MW are of the same order, that will be a constant. Actually, if you sent MT to infinity, you would see that it's not decoupling. And actually that's because you can explain that by saying that actually for this diagram here, if you have if you consider the coupling of the top with the W in the high energy limit, actually you have a coupling that will go like the mass of the top. That's because you've got this longitudinal polarization of the W that goes like a Higgs contribution, actually. And so that means that you don't have decoupling in this limit because of this coupling that goes like the top quark mass. And so that explains why, in the end, you do find this kind of situation where the contribution goes like a function of mi squared over mw squared. But so that means that this structure, so you have a separation and the fact that the top contribution is the most relevant. Okay, so now I think that let's see, well, I wanted to say for the moment for the neutral currents. Okay, so just to do a bit of a recap here. So, and actually, I didn't spend too much time on this actually, but I can go now. So you see that if you look at the flavor, you've got quite a large number of parameters which are set to arbitrary values in the standard model. So you have the fermion masses, and this, you know already that the values are very arbitrary with a huge number of, a huge hierarchy between the various values. And actually you've got also this mixing matrices between the generations. So you've got the CKM, and then I've also the PMNS, even though I didn't discuss, as I said before, the number of parameters needed depends a bit on what you assume concerning the values of the mechanism for the generation of the neutrino masses. But at least if you, if you're assuming that you're doing exactly the same thing for the neutrino sector as for the quark sector, you would have also the same number. So you've got quite a 6, 4, 4 here. And then you see that it's a much larger number than for the gauge sector. So you've got only your free coupling constants, or the Higgs sector, where you do have the parameters of your potential. Obviously, to get a better handle on this, so you can imagine two things. Either you say, well, which are not incompatible. One thing is just to say, I want to understand better the source of this arbitrariness. But to understand that better, clearly, we need first to know exactly the pattern that we want to reproduce in the standard model. So this is clearly, and that's the first step in any case. Even if we were not interested in explaining it, at least we need to know it in very much detail in order to be able to make predictions within the standard model. And then the thing is that because of what I discussed, so we saw that for the charge currents, you got naturally a question of CP violation that comes naturally. And actually there is one, as I said before, one source for the fermion sector. So that means that, contrarily to what I said just before, for this part of the standard model is very predictive. And so that's very interesting to try to check whereas it is indeed giving an appropriate description. The second thing is that this is also an interesting constraint on new physics models, because if you want to extend, then in general you have many potential sources of CP violation coming in. And since I said just before that the standard model version is very much constrained, then that's a very powerful tool in order to put constraints on the new physics model. The second thing is that the neutral currents. And so, as I said before, they are very much suppressed. So you might think that it's not really worth the chase, but actually they have the advantages of the drawbacks, meaning that you will be able to use them as they have a sensitivity to high energies. Already, just by my discussion in the standard model, I showed you that there was a particular sensitivity to the top quark mass. And so that should be the same for other modes, new physics modes that can enter the loops. And so that means that they can be very interesting to study for this reason. So enhancing potentially some of the currents. And actually, that's going to be the things that we're going to discuss. So at some point, I will just, so as I said before, I will have for the next session some tools, theoretical tools to deal with this. Then the CK matrix, and then the anomalies that more or less correspond to exploiting in different ways these aspects of the charge currents and the neutral currents in the standard model and beyond. Okay, I think that's already enough for today. Thank you very much.